So how do our carbohydrates fuel our muscles? I think most people understand that our muscles fuel our movement, but if you actually stop and think about that for a second, it's actually pretty incredible.
You ain't been to the education. You don't realize I'm so frustrated. You ain't got the answer. You ain't got the answer.
Our muscles move our bones and joints into position whenever we want and however we want. We can perform amazing movements in life, sport, and competition. And not only this, we can perform exactly how fast we want the movement and to what degree. It is incredible. Here we have pieces of muscle protein that can move our body into the position without us really having to think that hard about it at the very instant that we think about it. You move your arm up, boom, it's there. You want to get out of bed, boom, you're out. You want to jump, run, swim, throw, row, sprint, tackle, push, or twirl backwards in midair, you can do it. So that's pretty amazing. But I think most people take for granted just how amazing this whole process is. And today we are going to take a look at exactly how carbohydrates move from our mouth and fuel our muscle work. But first, we actually need to understand how muscles exactly work. So really, all our skeletal muscle is just structural proteins put together from the food that we eat, organized in such a way as to allow gliding and sliding of the individual muscle fibers in order to contract and relax. So this is how we move. When we tell a muscle to contract, the two bones move closer together and across the joint we get movement. This process is called cross-bridge cycling and happen when the specialized heads on muscle filaments called myosin heads latch on to the other thinner part of muscle filaments and contract and shorten. And whilst at one myosin head it only may be a tiny amount of shortening, you add this over the entire length of a muscle and you have quite a large degree of shortening and movement that can occur at each muscle. But where do these tiny little heads, myosin heads, get their energy from? They are doing so much work. Where are they actually getting their fuel from? Well, they get their energy from something called ATP, one of the most important molecules in our body, adenosine triphosphate. And this molecule is so important that it allows us to perform work and provide our body energy across almost all of our cells in our body. And it consists of rings of carbon, nitrogen atoms, and a sugar molecule. But the most important part on this molecule is a string of 3 phosphate groups, and that is ATP, the tri being the 3 phosphate groups. And when ATP comes in contact with water, a chemical reaction occurs and heat energy is released from one of these phosphate groups breaking off. The resulting product is now called ADP, which is adenosine di-2-phosphate groups, and now it's actually a molecule that is not as high energy. So ATP is the key energy we need across our body to fuel our metabolic processes, and this is exactly what happens at the muscle. When ATP breaks off at the site of the myosin head, it provides the myosin head enough heat energy in order to contract onto the muscle and shorten it. Add this across the length of the muscle, like I said, and you actually get quite a shortened muscle and quite a lot of movement. But the question is, how do our muscles get this ATP and how does our body even create this molecule? Because one molecule of ATP only provides enough energy for one myosin head. So as you can imagine, we are going to need millions, if not billions, of this molecule of ATP just to fuel our processes throughout the day. We are going to need a lot of ATP molecules. And our body knows this. It knows that we need to make ATP from the fuel that we eat, which is the food that we eat. And carbohydrates is the key focus of today. So how do carbs get turned into ATP to fuel our body? Well, there are 3 main metabolic pathways for our body to make ATP, but it doesn't make ATP very much in the first 2 metabolic pathways. The first 2 metabolic pathways are actually designed to get the body geared up for the final pathway where it makes its return on its investment. So it does a long series of chemical reactions throughout the first 2 chemical pathways. So keep that in mind, that the investment doesn't come early, but these first 2 chemical pathways are crucial. It's like making an investment in order to then reap the rewards later on. What is the first pathway? The first pathway is called glycolysis, and it is the way that our body turns glucose, which is carbohydrates broken down to their simple form, into something called called pyruvate, and 2 ATP molecules are made through this long series of chemical reactions, but the key bit is a molecule called pyruvate. So one glucose molecule can make 2 ATP and 2 pyruvate molecules. Now you're probably thinking, what the hell is pyruvate and what does this have to do with energy? Well, pyruvate then feeds into the second metabolic pathway, which is called the citric acid cycle. The citric acid cycle takes the pyruvate that was formed through glycolysis and turns it into something called acetyl-CoA, which is another molecule. Now this is taking place instead of the cytosol, this is now taking place in the mitochondria of cells. But again, going through all the chemical reactions in this citric acid cycle only yields the body one ATP molecule from one pyruvate. Now this doesn't seem very clever. What the hell is the body doing? It needs ATP. Why is it making all these other molecules? Well, because from this citric acid cycle there are two coenzymes that are super important that are created. These are called NADH and FADH2. And why are these important? Because when the body has finally made these, it can move into the third metabolic pathway, which is called oxidative phosphorylation, or the electron transport chain. Now it does take a while for this third pathway to fire up. It's like an old slow computer. But once it is fired up, it is the big powerhouse of making ATP molecules. What is it? Well, it's a series of 5 protein complexes embedded into the mitochondrial membrane of cells, and it uses NADH and FADH2 as electron donors to fire up this entire process. So it actually uses the coenzymes FADH2 and NADH to pump protons, which are positively charged hydrogen ions, out into the intermembrane space, and this creates an electrochemical gradient that it can then use to its advantage. Because once it's pumped enough of these protons out using the coenzymes from the citric acid cycle, the electrochemical gradient is so strong that protons generally like to flow from high energy states back to low. And because the high energy state is now in the intermembrane space, all these protons want to flow back in now into the mitochondrial matrix. And the final protein complex, which is complex 5, likes to take advantage of this. It is called ATP synthase, and it is like a huge rotary motor, and it actually spins around when protons flow through it. It's actually the flow of hydrogen ions that creates enough energy to spin this motor around. And what does this motor do? Well, it actually takes ADP, adenosine diphosphate with only 2 phosphate groups, takes a phosphate and actually jams it back on. So it actually sticks these back together to create a new ATP molecule. So you can think of it like a factory machine putting 2 bits together to create an ATP molecule. So it takes an ADP, a phosphate that's just free and floating around, sticks them together, and suddenly we now have ATP, which has 3 phosphate groups again. So let's do some maths on how this all works. Glycolysis gives us 2 ATP molecules, 2 NADH molecules, and 2 pyruvate molecules. And those 2 pyruvate molecules get turned into acetyl-CoA and go through the citric acid cycle. So 1 pyruvate molecule gives us 3 NADH molecules, 1 FADH2 molecule, and 1 ATP molecule. But we get 2 pyruvate molecules, so really we get 2 spins at the citric acid cycle, which means we have to double our figures. So in reality, from 1 glucose molecule, we get 6 NADH molecules, 2 FADH2 molecules, and 2 ATP molecules. Not very much from 1 glucose at the moment. But then, like I said, these go through the electron transport chain, and that's where we get the return on our investment. Because from the electron transport chain, we can generate about 28 ATP molecules just from the products that we've got from glycolysis and the citric acid cycle. So you can see the third pathway is the most important for creating energy from glucose. So in summary, just from 1 glucose molecule going through all these 3 pathways, we get 32 ATP molecules, with the bulk of those 32 coming from the third pathway, which is the electron transport chain. Now you're probably wondering, what happens when the glucose runs out? Does our energy production stop? But we know that can't be true because we can exercise for hours and hours, and our body only actually holds about 600 grams of glucose or glycogen stores. So we know at some stage these will have to run out, but the body can't just stop us moving if we don't have glycogen stores. And this is where in part 2 of this video series, we will be speaking about how the body starts to keep our energy processes going without using carbohydrates or glucose, instead using other sources like proteins and fat. So we will be speaking about how fat comes into play and keeps us able to keep moving once the glucose and glycogen runs out, as well as how we can start to manipulate this in order to lose more fat during exercise. Thank you so much, guys. I really appreciate all your support. Fitness Science signing out.